Oh, I'm ready, as long as you're ready.
So welcome back to the Joint Algebraic Geometry Seminar. Today it's a pleasure to have Dawei Chen from Boston College and the IAS, who will be talking about something different, volumes and intersection theory on modular spaces of Abelian differentials.
Thank you. I want to thank the organizers for inviting me, and thank you for coming, especially for the evening talk. Okay, so feel free to ask any question if you have. So I'll start by, by the definition. So Abelian differential is a holomorphic one form on a Riemann surface. Are required to be non-trivial, just means it is not identically zero. So in that case, it has isolated zeros. So away from the zeros, so you can pick a suitable complex coordinate z to write omega as d of z, if at the origin it is non-zero. So you write z in terms of standard Euclidean coordinate x and y, then dz is dx plus I dy. So under this expression, so this xy coordinate actually induces a standard Euclidean metric on the underlying Riemann surface. So, and what happens as the zeros of this one form? Well, so let's speak of a zero of omega of certain vanishing order. Suppose I have a zero of vanishing order m at the origin. Again, by picking the suitable local coordinate z, because it is of order m, I can write down this one form omega as d of z raised to n plus first power. So if you d of it, you get some constant times zm dz. So it gives you the order m zero at the origin. And if you think about it, under the nearby flat metric, so if you see one copy of dz, then you should imagine locally you have one Euclidean disk. So here, the exponent is, if m is a positive integer, the exponent certainly is bigger than 1. So you should imagine you have n plus 1 many flat disks glued consecutively, like a branch cover ramified at the origin. So maybe to draw the local picture, it looks like this. And here you still have the flat metric downstairs, but your form, in this case, I guess, have a triple cover. It looks like d of z cubed. So where this is given by pullback u equal to z cubed, and you pull back du. Okay. So that's how you should think of the local flat geometry around a zero of this one form at a certain with certain vanishing order. So I'll also present you a global picture soon. But in this case, so because I glue n plus 1 many disks together, you should think of, OK, under the flat metric, you get actually a saddle point or cone point as a zero with total angle given by this exponent n plus 1 times 2 pi. So whenever m is positive, so this angle is certainly strictly bigger than 2 pi. So that means locally, you won't see a smooth point under the flat metric. You will see a saddle point. Okay. So let me show you a global example. So this actually, I claim, is a holomorphic one form with a double zero, a unique zero, but it's a vanishing order 2 on a Riemann surface of genus 2. So let's check this example, how it works. So I started from an octagon. So that is 8 edges in the Euclidean plane. So this is a special octagon with 4 pairs of parallel edges labeled under the same letters, vi with vi. So each pair of vi, they are really the same vector. They differ by translation, just adding a constant to one vi, you get the other. Okay. So under the identification of edges with the same labeling, all the 8 vertices actually becomes the same point after gluing. So you can easily check that. If you start from the left endpoint of v1, so you regard it as the upper endpoint of v4, so it identifies, the left endpoint v1 is the other left endpoint v1, which is the upper endpoint of v2. And then you identify with the left endpoint of v3, and then it becomes the lower endpoint of v4, and you continue this game. And very soon you see that all the 8 points, 8 vertices become the same point after identification. And this is not only a topological presentation of the surface, because we have more information. So the transition function are away from the blue vertices. They are all translations. If I take a chart here using the underlying Euclidean chart, and I want to look at the transition function by gluing this part of V1 to the other part of V1, certainly they differ by adding a constant by translation. So this change of coordinate, since they are translations, suppose I have z equal to z prime plus a constant, maybe let's do z1 equal to z2 plus constant. So these local coordinates are not globally well-defined. Nevertheless, if you differentiate, the differential is globally defined. So this tells you I can just consider omega equal to dz1, which is also equal to dz2, because the constant term is gone. So at least, so I get a well-defined global form away from the unique special point. Okay, so that's how you read off this flat metric or this differential form under such a picture. And what happens as the special vertices? So we have this algorithm or this correspondence between the zero order and the total angle. So if you look at the total angle around these blue vertices after identification, so it's an octagon. So the total angle is 6 pi. Right? And if you write 6 pi as 3 times 2 pi, okay. So this 3 tells you locally you glue 3 disks consecutively. So the form omega at this point looks like d of z cubed up to some non-zero constant. And this is really z squared dz. So where the exponent tells you you have a double zero as a special blue point. Because it's a, so this 3 becomes 2 plus 1, and this 2 tells you the zero order. So in general, so you have this very nice correspondence between holomorphic one forms and such polygon pictures. The only requirement you put on this flat polygon is that so after identification, you get finite many special points, and the cone angle at each special point is the integral multiple of 2 pi. And this integer multiple, if you subtract 1 from it, you just resolve the zero order of the one form. So any question about this example and the definition of Abelian differential? Yeah.
Is it clear that conversely, if you have a genus T surface, then you can find, and you have a differential with a double zero on it, then you can find such a polygon?
So if you have a genus G surface, then the total zero order will be always 2 times G minus 2, right?
Yeah.
So once you specify the zero order, so you may have some polygon presentation, but the polygon presentation is not canonical. For example, I can always cut it open and reglue. So in other words, you have to think of this polygon picture as that, maybe put it differently. So how do I get these edges, special edges? Well, you can view them as first topologically as some homology class in the underlying surface, and just integrate the form omega against them. You just get the complex vector vi. Okay. And the polygon picture actually is a little, well, it's very nice, but also a little confusing or could be misleading. For example, up to, so you may see a very thin and long polygon. However, you may just chop it off into many small pieces and then reglue. After reglue, under these translations, the new polygon looks like almost like a regular polygon. But that means the underlying differentials are really the same, or up to isomorphism. So, any other question? Okay, so we usually like to, or in geometry or in many other fields, we like to put geometric objects with similar structure into a parameter space called the modular space of such objects. So here we need to fix some discrete topological data to start with. So certainly I'd like to fix the genus G, okay? Moreover, so the zero order seems to be something discrete, right? So you have some zero order or some cone angle, and like to fix this data. So that means I consider Abelian differentials of the same zero type with n distinct zeros, and each zero has Vanchian order mi. Mi is a positive integer. So you can check that for the non-trivial abelian differential on the genus G Riemann surface, closed genus G Riemann surface, the total zero order must add up to be 2 times genus minus 2. So that means I need to pick, when I say that I fix the zero order, that means I choose a positive integral partition of 2t minus 2, denoted by the signature mu, so which is consists of m1 up to mn n positive integers whose sum equals 2t minus 2. So I always fix this mu. Okay. Well, then I just consider abelian differentials of type 0 type mu. First, I define as a set this curly h mu, parameterizing all possible abelian differentials of type mu on Riemann surfaces of genus G up to the obvious isomorphism. Okay. So this notation omega parenthesis 0 just means omega has n distinct zeros labeled by z1 up to zn, and each zi has Vange order mi. Okay. So if you are abelian, that means the canonical divisor associated to omega is of this type. So here it's really important that you require all the zi's are distinct. Okay. So far, this is only a set. So why do I call them strata? Well, if you consider the union of all of these h mu, okay, regardless of zero type, but fixed G, what you get is the following, maybe rather more familiar object.
Question, sorry.
Yeah, go ahead.
The zi's are not fixed.
Zi is not fixed.
So I can imagine x with the zi's and omega, like
Yes.
mgn.
Yes, you could think of this way. So in other words, if I know the form, certainly that determines the underlying zero.
Yeah.
So in other words, the only data you lose by looking at the underlying zero is rescaling data. You could think of this as modulo C star. I'm going to talk about it. It's almost the same, just parameterizing canonical divisors of this type. The zi's are not fixed, but they are rather special points in X, yeah, so that their sum with the weight mi give you a special canonical divisor. For example, you could think of the most special one when n equal to 1, and there is a single entry 2t minus 2. So that means this is unique zero of 1 order 2t minus 2 give you a canonical divisor. That's rather special. Yeah.
Thank you.
Other question? Okay, so let me explain why they are called strata. Just because if you still fix G, you take their union. We consider all possible partition of 2t minus 2. In other words, regardless of zero type. That means you pick any genus G Riemann surface and look at the holomorphic one form of arbitrary type. And what you get is just, so the modular space of genus G Riemann surfaces is a modular space denoted by mg. And then fixing a genus G Riemann surface, there is a G-dimensional vector space of holomorphic one forms. And this G-dimensional vector space varies with the underlying complex structure, and they form the so-called Hodge bundle, which is a rank G bundle. And if you require the differentials are not identical 0, just remove the 0 section. So in other words, this H mu, they stratify the Hodge bundle by their 0 type, because if you take the most general partition given by 1, 1, 1, 1, that means you pick a general one form or general canonical divisor. You expect it to have simple zeros only, right? Just like a polynomial, usually pick a random polynomial, you expect simple roots. And here, if I have two zeros, maybe they're arbitrarily close and eventually they merge. I'll get a double zero. That means the signature specialized from 1, 1, 1 to 2, 1, 1, 1, 1. So I get to the next strata. And then from then on, I could either merge a double zero with a simple zero, I get 3, 1, 1, 1. Or I could merge another two simple zero, I guess 2, 2, 1, 1, 1. In other words, the specialization of the partitions induces the stratification of the Hodge bundle. Okay. Well, but still, everything is heuristic, because when I just define this H mu, it just looks like a set. How do I give it any geometric structure? I mean, well, nevertheless, there is a really nice geometric structure associated to each H mu given by period coordinates. Let me quickly explain. So what I'm going to do is that, so I start from a point that is x omega as a point in this strata H mu. In particular, omega already is of type mu. It has n distinct zeros, Z1 up to Zn. Now I label them just as marked point in the surface. I consider the relative homology group H1 of the surface X relative to the n points. Draw another picture. So this is a topological picture. Suppose I have, maybe I put Z1 here, Z2, and Zn. And if I don't have these marked points, then I get 2G elements for the absolute homology. And then with these n points, the relative homology has additional n-1 paths connecting n-1 marked point to the last one or the first one. So in any case, so the rank of this relative homology is equal to 2 times genus plus the number of marked point minus 1. You can easily compute it. Well, once you have this chosen basis of the relative homology group, what you can do is that you have the form omega. You just integrate it against this basis. You just get 2G plus n-1 complex number. And I claim that actually this 2G plus n-1 complex number, they really control the deformation of the form omega while preserving its zero type. So here's a heuristic argument, just because these integrals actually really control the shape of the polygon. So let's come back to the original picture. So here, if you think about it, this is a genus 2 surface, right? So I only have 1, 0, so there's no relative homology, only absolute homology. It doesn't matter. So if you think about this VI, they actually really form a basis for the absolute H1. And you integrate omega against each path, you just get that complex vector VI. Now let's deform these vectors a little bit. I perturb VI a little bit to make sure the polygon does not break, does not self-intersect. Well, then it remains to be octagon. And the gluing pattern is the same. After gluing, you still get one special point, and the total angle remains to be 6 pi. So in other words, this perturbation of the edges or those integrals really preserve the zero type of omega. So if you think of this as a somewhat convincing explanation, then we deduce a quick consequence. Let me go to the key point. Because I really have 2G plus and minus 1 basis element, and they control the deformation of this polygon, deformation of this form, while preserving the zero type. So they actually induces a complex structure for the space H mu. And the complex dimension is equal to the rank of this relative homology group, which is 2 times genus plus the number of zeros minus 1. So in particular, sorry.
Why is orbifold?
Oh, the same reason as why the modular space Mg is orbifold, because some special surfaces may have additional automorphism. Like think about like even for genus 1, right? There are like orbifold points. So here's a similar thing could happen. You may have a surface along with a one form altogether as a pair. It has additional automorphism. Yeah. But modulo that technical issue, if you think of it as a complex manifold, is okay. So you have these standard complex structures coming from the pure coordinates.
But is that, all the orbifold structure coming from Mg?
No. So because it has additional forms, right? So you have a pair, you have, so it's a similar but different automorphism, right?
Okay, you can introduce a new.
It must be the automorphism of the underlying surfaces that also induces the automorphism of the form, right? Yeah, it is more restrictive. Yeah. Any other questions? Okay, so let's go to the topic about volumes of this modular space. But before I do that, I think maybe for some of you, well, let me recall very briefly a similar story, which actually might be more familiar to some of you. It is about the correspondence between V-Peterson volumes and Witten's conjecture. Okay. So I'm not an expert on this, so I'm only recalling it as an analogy to compare what I'm going to tell you later. So Woppert shows that, so from the technical space, there is a somewhat very natural standard symplectic form which induces which descends to the modular space of Riemann surfaces with n markings and extends to certain convocation using nodal Riemann surfaces called the Deligne-Mumford convocation. And the key point that Woppert actually shows that this symplectic form extends and corresponds to up to modulo some pi power rational cohomology class, or like some Chen class, the Mumford-Chen class kappa. Even if you don't know the definition, it does not matter for the rest of the talk. You only need to know there's a correspondence from something more analytic from the technical side, which gives you some symplectic Wellman form, and then you can relate it to something algebraic as a Chen class or rational cohomology class kappa. So once you have this correspondence, and you want to compute, say, the associated volume of this Deligne-Mumford modular space MGN, then it amounts to take this algebraic class kappa and raise it to the top power of raise to the dimension of the modular space MGN. And indeed, Morzahani generalizes correspondence a little bit further. So here, when I talk about MGN, the n points are really n markings. But Morzahani considered, okay, let's open up these n markings and consider the Riemann surface equipped with hyperbolic metric. So we require the n opened up boundary components are geodesics under the hyperbolic metric, and require them to have specified geodesic length given by this length b, which is a sequence of n non-negative real numbers corresponding to the length of these n boundary components. Under this setting, you can naturally define similar modular space parameterizing these hyperbolic border Riemann surfaces denoted by MGN bar B. And this symplectic form also corresponds to a deformation of the original kappa class by adding a linear combination of some famous psi classes, which I'm going to explain. But just let's focus on this. So you again have some correspondence between some symplectic form and an algebraic class, where you have not only the Mumford kappa class and some linear combination of psi classes. So what are the psi classes? They play a role for later part of my talk, so let me recall the definition. These are really the same psi classes that shows up in the most famous Witten's conjecture in, I guess, in early 90s. But in any case, so psi class comes from, so here I have n marked points. There are n different psi classes for I from 1 to n. So this is the first Chen class of some holomorphic line bundle Li. So what are these line bundles Li? So Li lives on MGN bar, okay? So the Deligne-Mumford modular space, if you don't know Deligne-Mumford, just think of the modular space of Riemann surfaces with n marked points. And the fibers of Li over each point, suppose I take a point x and z1 up to zn. So the fiber of Li is really given by, canonically given by the cotangent space of the Riemann surface X associated to the ice marked point. Okay. So these are the fibers of Li, and these cotangent spaces, they naturally vary with the underlying Riemann surface and the marked points. The thing is, these marked points are always in the smooth locus of the Riemann surface, nodal Riemann surface. The tangent spaces are always well defined. So you get a holomorphic, complex one-dimensional holomorphic line bundles over MGN or MGN bar. You take its first Chen class, that is a so-called psi class. You get n of them. All right. Then once you have this generalized correspondence, you can still compute the V-Peterson volume of these Riemann surfaces, modular space of Riemann surfaces with hyperbolic boundary components, just as the top intersection number of this Chen class. You raise to the dimension of this modular spaces, 3g minus 3 plus n, and you expand it, you get a bunch of monomials between the kappa class and psi classes, as long as the exponents add up to be the dimension of the modular space. So this is somehow very similar to the result I'm going to tell you later. So I will also use these psi classes, and I have another class that plays a similar role to the kappa class. Okay. So that's really a correspondence I'm going to mimic and tell you. But anyway, so what's the relation to Witten's conjecture? So Witten conjecture is about, you just take these psi classes and consider all possible top self-intersecting numbers over the Deligne-Mumford space MGN bar. Then you get a lot of numbers. But if you package them in a generating function, like G, N, and these exponents vary, and Witten conjecture and motivated by some intuition from physics, Witten conjecture these generating functions satisfy special differential operators called some KdV hierarchy. And Mirzakhani used this connection to the V. Peterson volume, and then brought in tools in hyperbolic geometry to study this hyperbolic boundary component, how they bound pair of pants decomposition. And she obtained a recursive formula that actually, as a consequence, proved Witten's conjecture. So I'm not talking about the combinatorial part in my talk today. So I'm really focusing on the geometric correspondence from some volume of a modular space to intersecting numbers. That's the part I'm focusing on. But I think this is a nice story to introduce. Okay.
The Kappa class is the C1.
Not quite. Kappa class is C1 of the push forward the dualizing Lamb-Bondor square. So it's not quite the C1, the Hodge class is usually called lambda. But it doesn't matter because I'm not going to use kappa anymore. Yeah, only as an analogy to recall the story. So kappa is not my player. That's Mirzakhani's. Okay. And there's, one technical issue one really has to consider before doing any kind of intersection theory. Right? Because you see, I really passed from the original MGN to MGN bar because whenever you want to study any intersection number, the modular space has to be compactified, right? So I cannot just talk about intersection on like an open quasi-projective variety. I need to compactify it. So let me briefly say that where we do intersection calculation. So I originally introduced this H mu space. So clearly there's no way for H mu to be compact for two reasons. The first, so as you already asked, so I can rescale the form to make it arbitrary large, arbitrary small. So it's unbounded like a vector bundle, right? Even if I mod C star, projectivize it, it seems like better. Nevertheless, the zeros can still collide, right? I may change my zero type. Maybe I change from a simple 0 to double 0. That means I really change my strata, go to like a lower strata. That's not good. And moreover, even the zeros remain distinct, my underlying Riemann surface may become nodal, right? There are several issues I have to deal with. So well, luckily, we already have the Deligne-Mumford modular space. And the Hodge boundary itself behaved pretty well over the Deligne-Mumford space. So I can naively do the following setting. Let me see what is here. OK, so let me explain this very brief sentence. So I have the Deligne-Mumford modular space, MGN bar, to start with. Okay. So let's first consider all holomorphic one forms and projectivize it, just mod C star. That's OK. Well, luckily, even if I have a nodal Riemann surface, if I replace holomorphic one form by something so-called stable one form, or the canonical Lamb-Bondor by the dual length Lamb-Bondor, I take the global section, I still get a G-dimensional vector space. In other words, the original Hodge bundle extends and remains to be a rank G bundle over MGN bar, over the Deligne-Mumford boundary. I can just add a bar here, so I get a nice vector bundle. I still projectivize it altogether. I get a project bundle whose fibers are PG-1 over MGN bar. Okay. So here, I have my stratum H mu. I projectivize it, OK? And because I lift it, so I have n. So mu is a zero type of n distinct zeros. So I can just mark them. So I can think of my underlying surface is of genus G with n distinct marked points, right? Certainly. And I have a form, omega. So everything lives inside the projected Hodge bundle over MGN bar. So I have a projected variety. I can have a quasi-projective subvariety. I can simply just take its closure, whatever it is. I take the closure. I just get some closed subvariety. So that's the modular space compactified strata I'm going to use to carry out some intersection calculation. OK, so that's my notation for this PH G gn bar mu. So exactly this guy. Okay. So it somehow takes care of the issues we worried at the beginning, right? So I projectivize it. As the n-mark point, I take the Delimonfort boundary. So basically, everything becomes compact. Okay.
But still, I mean, is the zero of differential allowed to along the mark point?
So zeros of differentials, if I start from here, the n zeros are exactly the n-mark point, right? But when I take the closure in the boundary, you have to think a little bit. Yeah, because you may have a form that is identically zero when your Riemann surface become reducible as some component, right? But there, it may carry some special zero, and you may ask, where are the positions of zeros? Because your forms is identical zero on some component of your reducible Riemann surface. Everything zero on that component, so where are the limit zeros? So we need some understanding of the boundary. Let me just briefly say that with my co-author Spinbridge, Yang Hong, Grosetsky, and Moller, in an earlier work, we actually can describe the boundary of this codification to answer the question, for example, you asked, how the boundary differentials and the limit zeros look like. But again, so we don't need it for this talk. I only need to convince you there is some connectified modular space existing. That's good enough. In order to use it to do some finer calculation, so we do know some information, and that's enough for the calculation later. Yeah. If I talk about the complication, it would be a different talk, so let's skip the details. Okay. So any question about this part? Well, this settled one issue. We have a compacted modular space, but I still haven't told you what volume I want to compute, right? So volume is called means the Rich volume for the modular space of differential. So here's actually an interesting part. So I take a point, x omega, where omega is this one form. And if you think of omega as dz, and you write omega wedge omega bar, right? That is dz wedge dz bar. And you switch it to xy coordinate, you get dx wedge dy bar, but there is some coefficients, roots of -1/2. Right? And if you integrate dx wedge dy bar, sorry, dx wedge dy, you certainly get the area of your domain surface, right? So I'm saying knowing this one form under the induced metric, you can use it to compute the area of the polygon picture you saw earlier. It's very easy, right? So this is an area form for a given differential to compute the area of the surface under the metric of omega. Well, so my space H mu itself is unbounded. So if I want to consider a finite volume, I rather need to pass to some bounded domain. In other words, if you have a vector space, you want to compute the volume. It's impossible to have a finite volume. Nevertheless, if I pass to a hypersurface, like a sphere in R3, then I have a much better chance to have a finite volume. Right? So here we do the same thing. How do you pass from, say, a vector space to a hypersurface? I could just take a real codimension 1 hypersurface by imposing the condition that I require those surfaces to be of area 1. In other words, I consider the h lower 1 mu to be h mu mod r plus. Then I can pass from this sort of a vector space picture to a real codimension 1 hypersurface, just by normalizing the areas of flat surface to be area 1. Okay. Well, then I still need some measure of volume form in order to speak of a volume. So let's recall that this space H mu has a local coordinate system, right, given by those integration of omega against some path. They are called pure coordinates. So that means locally I can model my space H mu as a standard complex 2G plus n minus 1 dimensional space. I just take the standard Lebesgue measure from that vector space, just standard Lebesgue measure. And when you change your basis of this relative homology, the change of coordinates differ by, because I'm taking the integral basis, the change of coordinates actually preserve this measure. So you get a well-defined volume form, which also pass to the real codimension hypersurface you get under the natural Lebesgue measure. And then this volume is called the Miseevich volume for the space H mu. Okay. In other words, the key point is that I have local coordinates So I just use a local coordinate and the standard Lebesgue measure to define the volume form. And the associated volume is called the Miseevich volume. Everything is really supernatural. I have local coordinates. These local coordinates are compatible under changeable basis, which preserve this standard Lebesgue measure. So I just look at the associated volume that is called the Miseevich volume. Okay. So the question is, how do we compute it? So this seems like to be defined in a very transcendental way. Right? Period coordinates are usually not algebraic. And these spaces are still, in this setting, I'm not compactifying. And the coordinates may not extend to the boundary. So it's unclear. So nevertheless, so let me quickly tell you the main result, and hopefully we can finish in 15 minutes. I will. So let's see. It's getting late. Well, I just need to recall. Actually, I don't even need to recall because the psi class is still on the blackboard. So recall that the psi are the first chain classes of this Li bundle associated to each mark point. These are the same psi classes. It's coming from the cotangent spaces of each mark point of the underlying Riemann surfaces. But you put them all together to form the line bundles and the vector on the modular space and take the first chain class. I only need one more class, as I promised, to replace the rho of kappa. So that class I call it eta, which is also sort of natural, because if you think about it, I start from the projected Hodge bundle, right? Well, let's forget the bundle structure. Let's think of, suppose I have a projected space. Then it has a natural line bundle, tautological line bundle called O-1, whose fiber is just spanned by the underlying equivalent class of that vector. Right? In other words, I have this O-1 class, which is a line bundle over the projected Hodge bundle, whose fiber over the point, or a point is the equivalence class of x omega, where omega is regarded modulo C star. This fiber is just given by the linear span of omega. Okay, I have a one-dimensional fiber spanned by the point I'm the vector I'm parameterizing. Now you only need to do this relative version. So this fiber-wise is the same as the tautological line bundle class of a project space. Now I have a project bundle. I still have this O-1 class by collecting these tautological fibers together. So it's a holomorphic line bundle over the project Hodge bundle. I take its first chain class and denote it by eta. Okay. So eta is the first chain class of this class. Okay. So eta is a holomorphic line bundle on the entire space. Certainly is restricted to any subvariety. I can also regard it as a first chain class on this compactification. Okay. That just restricts the line bundle to subvariety. It's the same. All right, now we have all the ingredients to state the result. It's a quite recent result. The joint work with Martin Müller, Adrian Savicki, and Don Zaghi. So the paper was on the archive about 2 months ago. It says the following. So for any zero type omega, which is a partition of 2g minus 2, I have n zeros. So the volume of the strata I just introduced in the previous slides actually can be computed by the following intersection number. So which looks complicated, but let me explain to make sure at least the formula is readable. So the left-hand side is nothing but the volume of the stratum I want to compute. I just introduced there is some volume I want to compute. Okay? So let's just focus on the right-hand side. So the first term is some combinatorial term, right? There's some 2 pi I exponent, 2g, and there's factorial term. But these are just given by the signature. Yeah, so let's ignore it. And so this integral sign just means I want to compute the intersection numbers of these classes over which space? This compactified strata, that space. So that's where the intersection calculation happens, just over this space. Okay. Let's work out the dimension of this space. The complex dimension of the space is, so originally, if I don't project-wise, it's 2g plus n minus 1, right? But now project-wise, I subtract one more dimension, so it becomes 2g plus n minus 2. But let me write it this way. 2g minus 1 plus n minus 1. Okay. In order to get a finite number, I need, in total, this many first chain classes to multiply together. So here I have eta 2g minus 1 in the formula. Here I have psi 2 times psi n in the formula. Altogether, I get exactly 2g plus and minus 2 Chen classes, first Chen classes. So their intersection product gives you you just take the degree in the zero-dimensional cohomology, you just get a number. So at least numerically, it makes sense. And you may question me that, so this intersection number does not look symmetric for the endpoints, right? Because you see, I intentionally skip psi 1, and I only put psi 2 up to psi n. There must be something wrong. Nevertheless, so these zeros, they have different weight given by zero order. So I compensate by skipping psi 1 by adding also a asymmetric factor, this 1 over m1 plus 1. In other words, there is a secret relation I did not write on the slide. But you could skip any other psi I class, but then you have to replace this coefficient by 1 over its Wanshian order plus 1. So there are secret relations sort of given by mi plus 1 times psi I. It's almost the same as mj plus 1 times psi j. So when I say almost the same, is that this relation literally holds for these two line bundles or for these two Chen classes in the interior of the strata. Nevertheless, they differ by some boundary divisor because I compactified. However, the difference of them is eliminated in the total product. So if you take this intersection product, so they do not make any difference. But that requires some argument. So it's not too hard to see, nevertheless. That explains this asymmetric expression of the intersection number. I could write it in a more symmetric way, even by maybe adding some psi 1 here and lower down one exponent for eta. But I prefer this expression just for the following reason. I will show you in a quick heuristic argument to prove it, just in basically like one slide. But it's only a heuristic argument. It's not the actual proof. For that argument, so this formula makes most sense. But before I tell you the heuristic argument, any question about the formula? So I want to make sure the formula makes sense. Yeah?
So you're saying intersection numbers. So these classes are basically subvarieties, and their intersection number is some integer?
Yeah, well, rational numbers. Yeah, so you could think of this, if you don't prefer intersection number, you should think of this eta and psi I, they're all rational second cohomology classes. Okay? Okay? That's the same. You do the intersection in the cohomology ring. And they are even dimensional, so it doesn't matter for the cup product.
Why does it come out rational instead of
for several reasons. First, there's an all-before structure. Right? Yeah, so that's maybe the most important reason for them to be rational. Yeah, because the modular space usually they come from assuming you have a universal family, but if your modular space is not a finite modular space, you have to pass to a finite cover to have this universal family. So that means only after this finite base chain you get an integral class, but you have to divide by the degree of the base chain. You go down, you get a rational class. Yeah.
So in the volume, it's positive.
Oh, this number turns out to be always positive. Yeah.
Positive.
Yeah.
So, but eta is C1 of the universal template. So
Eta itself has no positivity property, neither like a minus eta. You can see by looking at this. So 2 pi I is root of minus 1, right? I guess minus 1 raised to the g. That tells this intersection number actually, in some sense, I'm going to explain. So this eta or this power usually comes from some symmetric form that has signature like almost g minus g. So there's a minus g raised to the minus 1 to the g's behavior. Yeah. So this eta has no positivity property, neither like minus eta. So yeah, so it could be positive, could be negative. It alters with the parity of g.
but psi also has no.
Psi usually has positivity property. Yeah, psi intersecting with any subvarieties, so the cycles or intersection number remains to be non-negative. But this eta is not. Yeah. It's a good observation. Another question? Yeah, go ahead.
So the manifold, the variety of integral over, it's a singular in general.
It's in general singular, yes.
Yeah, but it's closed.
It's a compact subvariety, yeah, closed.
Compact
Yeah.
Yeah.
It's a projected subvariety.
Okay.
Yeah, so in other words, you could think of, okay, so I still have the subvariety. on the blackboard, right? So you can think of, so the project Hodge bundle is something pretty nice. The project bundle or MGN bar, right? You could think of, because all the lamp bundles are introduced, they actually live over the total project Hodge bundle. You can think of this interesting number as intersecting with the cycle class of that subvariety. Like you can have a very singular curve inside the Pn, you can still ask its intersecting number with hyperplane ranges by degree. So you can think of that way. It does not matter for the singularity of this variety. Okay. Once you know the cycle class, that requires some calculation. Okay. Let's just do the heuristic argument and let's finish the talk. Okay. This is the best part I like. The heuristic argument via Hermitian matrix. So let's recall the volume element on the strata. Because now I projectivize it on modulo C star, right? I'm actually losing one like a local coordinate. Originally I have 2g plus n minus 1. Now I have 2g plus n minus 2. For simplicity, let's assume that I set one of the absolute period to be 1. Okay? So I only have 2g minus 1 absolute period. I set one of them to be 1 to take care of this projectivization. Then for the remaining 2g minus 1 absolute period, coming from the absolute part of the homology of the underlying surface, I denote them by A1, A2, up to A2G. So the volume element, because I have my local coordinates, and you have like something like A, B, C, D as your local coordinates, the standard big measures used by dA, wedge dA bar, and wedge dB, wedge dB, PGB bar, so on and so forth. Right? Here, this absolute coordinate gives me part of the volume element just by taking their dAi, wedge dAi bar.
Can you explain what you mean by absolute and relative?
Oh, absolute just means
Meaning the closed curve with the ending.
yes, yeah, just like h lower 1 of the surface. I take a standard symplectic basis. Yeah, the absolute. Because when I introduce the local coordinate, I have additional n mark points, right? So I have the other part denoted by Ri. So maybe it's better to recall the picture if it's still on the blackboard. So right here. Okay, I may have some absolute period given by some maybe Ai and blah, blah, blah. And these are my R, R2, R2, Rf. Okay, so Ai is as absolute period, and R's are as relative period. So this, sorry, I should denote by the path, but these R's are integral of omega against this relative path. You just get a bunch of relative cohomology, sorry, relative period denoted by Ri. So you take their wedge, and that gives you the other part of the volume element. You take the total wedge, that certainly is the standard volume element you get. Once you have this, so I claim this part, this eta 2g minus 1, really corresponds to the first 2g minus 1 wedge for the absolute part. Okay, so here I intentionally separated the volume element into two parts. The first part denoted by this dAi. Okay, I have 2g minus 1 of such. They really correspond to this eta raised to 2g minus 1 up to some normalizing factor. That is those factorial, well, this 2 pi I power. The reason is that to this lamp bundle, this tautological lamp bundle, carries a natural Hermitian metric just induced by the area form. Okay? So let's recall this tautological lamp bundle has fiber point just given by the form omega, right? Omega is a differential. I introduced the area of the surface by using the integral of omega wedge omega bar, and then by some standard Riemann by linear relation. If I know the pairs of omega, that is the integral of omega against symplectic basis of the Riemann surface, then I can use these pairs of omega to represent the area of this omega. So these are exactly this integral of omega against this basis of the absolute homology of X. And you see, I mean, here it really captures all the absolute period. And you take the standard dd bar log, the Kähler potential, and raise to 2g minus 1 power. Then you will get the absolute part of the volume element with some normalizing factors, as where you see the 2 pi I power and the sign. Okay, so that explains really the absolute part of the formula. So naturally, you would expect that now I have the additional relative part connecting, say, 1, 0 to the remaining n minus 1 zeros. And here is the heuristic argument comes in. So you should think of these psi I classes because they are the cotangent lines, cotangent spaces associated to the ith mark point. So when the ith point, mark point varies, so you should think of their variations governed by the psi or the Li bundles. So in other words, we would expect that one can find some Hermitian metric on those psi bundles so that if you do the algebra log and write them together, that may cover the relative part of the volume element. If you can do that, then you are almost done. And there's still one more step of technical subtlety because everything so far is in the interior of the module space. I still have to make sense of how this Hermitian metric extends to the boundary of my convocation. Right? Usually when you extend, if you do this metric thing, you know there might be something called like good Hermitian metric, and you have to control their Poincare growth on the boundary. So that's the final technical issue one has to conquer. But anyway, just make another connection to Witten's conjecture. Kontsevich gave the first proof of Witten's conjecture, interpreting these psi I classes as some kind of polygon bundles around the n mark points, using also some kind of differential, but not quite holomorphic differential, some quadratic differential with double poles. And anyway, so if you think of if we were Kontsevich, so our heuristic argument would be done, right? We don't have to do any more details. Well, so in the last 1 minute, so let me just say the outline of the actual proof. So if this were only heuristic, our paper would be like 30-page shorter, but now it's like 70-page long paper. So the actual proof is very indirect. We do it by recursions. We cannot directly say that, okay, there are such Hermitian metrics and extend to the boundary, you can control their boundary behavior. We are doing that, but still not there yet. So the actual proof is by recursions. So you show that the intersecting numbers on one side satisfy some recursion. The recursion really arises from merging two zeros so that you can go to a more specialized strata. So the zero type changes to something more special. On the other hand, you show that the volumes also satisfy another recursion. So that really is a very different technique. You have to interpret some special lattice point inside the volume, inside the strata under the period coordinates by counting some special branch covers of tori, and look at their asymptotic behavior. So once you have these two strategies to come up with two recursions, you show that these two recursions are equivalent. So one determines the other. And they also agree on the minimal strata on the base case where you have a unique zero of total vanishing order 2g minus 2. That you can have to do by hand, by indirect argument. It's like an induction. You have two system recursions, two system numbers, you show that they determine each other, and they agree on the base case, so that they agree for every case. So that's it. Okay, I think let me stop here.